Hi everyone, the amplifier project is complete and it works outstanding. And when I mean outstanding, I mean it works very, very well. Now, there's a lot of things to explain in this amplifier for those of you that are going to try to build along and build this amplifier. Again, I'm going to warn you, if you build this is at your own risk. There is high voltage in this unit because of this large transformer. And of course, there's mains exposed here and everything like that. So definitely don't build this if you're not confident or you're unsure. So again, if you're following along, you're doing so at your own risk. Be very, very careful. So this amplifier, again, I tried to stay away from using any type of circuit board in here because this is, I'm trying to keep this as point to point as possible. And I really struggled with this one little transistor stage amplifier. So in order for me not to use a circuit board, I fit the transistor into some remaining traces and then cut some traces so that I could just use the existing board. Now, it could very, very easily be returned. If you remove all the components, you can see where the cut is, and you can just scratch some of the coating off here and then just bridge it with solder in one or two places, and the thing would be absolutely fine. But again, I wanted to stay away from using a circuit board, and that was actually very, very difficult. Just because this capacitor here, it needed a filter in this area, and as you can see, the capacitor is very large. And I stood it up off the board so that I could solder it to the top side, because everything, all the modifications, aside from the original capacitor replacement, are all done from the top side, because once this is built with the heatsink in here, the last thing you want to do is remove this board. Now, if I was going to build a second one of these things, what I would do is I would measure where these two screws are on the other side of the chassis, and I would drill two holes here. So there would just be two holes. And that way, if this board ever needed to be serviced, what could be done is this screw could be removed off the regulator. You could remove these two screws here on the circuit board, and then you could remove the two screws down here that hold the sink. You could slide the sink out sideways and then just tip the board and remove the board. That would be an advisable thing to do, just in case you ever need to service this board right here. Now, I don't plan on having to take this out, and I don't really believe there's going to be anything that'll ever fail on this thing. That IC would be the biggest failure point in this, being overdriven and everything, right? Everything else here is just kind of idling along, really, now. And this transformer is, I guess you could say, going to see a pretty easy life now. So it's powering op amps and maybe the little display lights and the little amplifier here, and that's it. So this is, nice and easy on that. So you can see I've added the transistor in the bottom down here. I'll show you the schematic here in just a moment. I'll go over the schematic and some of the things that you need to know. So what I've done is I've just soldered the little transistor right into these existing traces down here. And you can see right over here, I put a cut in the trace. And I'll explain this all on the schematic, what I've done here in a moment. So there are some specific values in here, and those specific values are to make sure that the transistor is biased right. Now, when I was experimenting with this, I wanted to make sure that the gain was very close between the two amplifiers. All right, so it really just required one amplifier stage, and that was really it to bump that gain and make it just about perfect. Now, this amp has a touch more gain than the factory, just a touch more. And, it's probably desirable. Now, one of the nice things about this build is this has less hum than the factory version with the IC. So this is a very quiet amplifier aside from the front end hiss, because it's got a lot of gain stages in the front end, and there's a little bit of a shh noise in there all the time. It's just a little bit of hiss, and that's nothing I can do about that, right? I'd have to redesign the whole front end to get rid of that. But the hum was lowered, and that hum, one of the major things is their factory ground here. So this is their ground from the board, and you can see it runs into the trace down here. And this ground, I've put a little shield on it here, right? So the ground here would ground over to this area over here, factory. That's how that worked. So with this ground attached, the amplifier hums. Okay, it's not the optimum spot for the ground. So the new ground, which I'll explain here, is tied at this point on this trace here, And this is a piece of brown Teflon wire. It runs off and then it goes over here and it grounds to this point right down in there. So this is a ground to, you know, where the jack on the back for the biasing is grounded to, and then that diode is also there as well. So the difference between this ground and this ground is a lot of hum. So basically, if I was to attach this back to the chassis, it would be basically and that's the difference. Like it's a lot of hum. So I spent a lot of time moving the wire around the chassis and trying to locate the lowest point of hum. And it seemed to be right here, and it worked out to be right at the center tap of the filament for this. Now, by adding one more potentiometer and eliminating the center tap off the filament transformer and creating a system that you could actually move the ground around for the filaments, so it's across the filament connections, and you wouldn't have the center tap hooked up. You would have a 500 ohm potentiometer, and then the wiper would be to ground, and you could really fine tune the hum balance. You might be able to squeak just a touch more of hum out of there. Just a touch. It would be barely audible. Okay, it's that close at this point. Now, an adjustable hum balance is always desirable because you can really fine tune it. But this, as I say, we're running out of chassis space here. It's used up. You know, there's no chassis space left. Now, I put an external speaker jack at the back here and on the chassis, and I also put an impedance switch. So just in case I ever want to switch a speaker from, say, a 4 to an 8 ohm speaker, or if you want to unplug the factory speaker and plug in a cabinet and use an actual speaker cabinet for, you know, louder playing, that would definitely be desirable. You can just, flip the impedance switch here and select your impedance, and that is on the schematic as well. Now you can see that there is a lot of space between this and down the bottom here. As you can see, there's a lot of space there. So that way, if anything ever came loose or twisted, nothing would come in contact down here. We definitely wouldn't want that. Anything to come in contact down at the bottom here, because this here is the high voltage rectification circuit, and you wouldn't want to take any chances with that. So this is grounded, and it also, it's very, very tight on the back here. So lots and lots of room there. So if these were to actually twist, if that switch was to twist or the jack was to twist, it wouldn't come. Now the jack itself is above the negative bias section. It's actually not even above the high voltage section here. So this is even further away here. So a lot of planning there, just because there's not much chassis space left. You have to fit things in where you can. You can see they originally had some holes in the back here for a different amplifier option. And, there's, of course, it's way too close to the rectifiers at the bottom, so I didn't bother using that. You can see the signal line out, so the amplified signal line out. We're going to take a look at this on a scope here shortly, and I'll show you the signal path all the way through. So the signal comes out here, and then that just comfortably curves around here, goes through that coupling capacitor, and right into the grid of the phase inverter, and that worked out very nice. So no extra holes had to be drilled, just fit right through the factory holes. There's a lot of space there. That worked out well. This added a filter capacitor, which I'll show you on the schematic here, for the transistor amplifier is an absolute must, just because the filtering alone in the factory supply, even without the extra load, is still, it's on the verge of being just enough. That's the way they design things, right? So this one extra filtering stage is needed. Now, I soldered this on the top side of the board, so there's a bit of space under there, and that's why I shot some GE Silicone 2 underneath there, and then that holds the capacitor very steady. It's as steady as these ones, right? And that is definitely needed. Now, there's still quite a bit of space between this and the top, so there's no issues with this colliding to the top. Another thing that was a big thought is the handle on the top of the case. I'll just back out the zoom out here for a moment. The handle on the top side of the case where you carry this has a bunch of screws that go through the top, and they come down in about this area right here. That's another thing that had to be thought about during the build of this, is you don't want any components where those screws are going to get driven down into. And it's the same thing with these screws right here. Now, these are tight enough, even with the factory screws, that there is no way that this chassis would come out. You could drop this on the floor, the chassis would bend, and I don't believe it would actually come out. Those screws, they thread in here extremely tight. So that worked out very well. If you found that yours are stripped, which I don't know why they would be, but if you found out that you wanted to add a nut on the backside, that is possible. You would have to, what you'd have to do is file the bottom portion of the chassis here, and you'd have to solder either a brass or a metal nut onto the bottom side when nothing is in the chassis. And they also have those ones that you can put in from the top side, and they require a special crimper, and they would crimp down. You need a special tool for that, and I don't think it's needed. I really don't. Like, this thing is so tight. I could tighten those screws up to where it would actually probably, split the little washer on the top and maybe even, cause damage to the wood. It really is that tight. Another thing that needs to be kept in mind is you don't want to put anything under these, because those screws go quite a ways into the chassis, and you wouldn't want to put that screw through a line cord. So you have to make sure that that's far away. Same with here. You'll see that that screw is a long ways away from anything that it could collide with there, and the same thing in the front here. These are all things that have to be thought about when you're putting this together, because if you built, components directly under this and you drove a screw into it, that would cause some pretty big problems, especially in the high voltage section. So the ground, very important, very, very important when you're building this. It will be a terrible build if you don't put this in here, just because this board needs to be grounded, or you're going to be dealing with a moderate amount of hum, even out of that small speaker. This makes all the difference in the world. Make sure you ground it from that point right there. So basically just a little bit of the coating is scraped off in this area, nice and clean. So I used a small jeweler screwdriver and very, very carefully scraped the coating off, and then just ran a piece of wire down over into here, into this area. And that is tightened down right here by a little, basically an eyelet, grounding eyelet, right at that point right there. So that worked out very well. What else can I tell you about this that's different from the last time? I'll zoom on into this section here just one more time here, and then I'll get into the schematic, and I'll start explaining things on the schematic. So this here is part of the biasing right here, and you can see this resistor here is a 10K resistor, and that goes to the collector. That is a 2.4K ohm resistor, and you'll see this all on the schematic, and you'll be able to place this. This capacitor here has been replaced. You can see that C58 down there. This is needed to extend the low-end performance, so definitely do that. Add this capacitor. The values are on the schematic, and that's even listed there. So your schematic is right below this video. So you'll see a schematic there. It's in PDF form. The schematic that I'm going to be pointing to doesn't have values on it. Your schematic below the video will have all the values on it. So when you download that, you'll be able to see everything that is on my master schematic. No feedback was used in this amplifier at all, because it just doesn't sound nearly as good as it does without feedback. Looking at the frequency response on my Stanford Research SR780 in a sweep, very, very slight upkick rate just before it falls off at the high end. That's it. That's the only difference. When you add a bit of feedback, and I brought it to about 5 dB maximum, it flattened the response, and consequently kind of flattened the personality as well. So I didn't want to add any feedback. And that worked out really well, because if I did add feedback to it, it would have had to have another transistor amplifier stage, and I didn't want to add any more solid state devices to this. So it was either this transistor or a vacuum tube on the underside of the chassis. Again, no room left, right? So I wanted to do what was going to be easiest for all of you to find. I toyed with using a pencil tube. Basically, a pencil tube is what they used to use in the old hearing aids. And they're getting a little bit tough to find. I didn't want to do that, because I want to keep this as universal as possible so everybody can build this. Again, I didn't even use a circuit board, and that was a struggle, let me tell you. I wanted to screw a little circuit board right to the back side here and mount all the components onto that, and then just connect wires to the traces. But again, I wanted to keep this point-to-point for all of you out there that are wanting point-to-point. This is just a modified circuit board, scratched traces. You can see the traces is a split right there. And I believe that was, the only split trace. Here's the completed schematic for the amplifier. Again, your copy just below this video in the attachments will have all the values on it. There's a lot of writing on that schematic. One of the things I want to talk about is the fuse. The fuse that I chose for my unit right here is 1 amp, and this is an absolute value fuse. I don't want that fuse to go away unless there is some form of a catastrophic failure. Now, in order for me to come up with this value here, what I did is I loaded the amplifier to its maximum. So the amplifier was a wonderful square wave generator at about 16.3 watts, I believe it was, 400 cycles, and the draw on the line at that point was just under 600 milliamps. So that's 600 milliamps at around 120 volts. Now, in order to test this and to see what the current draw would be in a short circuit condition, yes, I have to short circuit things. So what I would do is I short circuited the high voltage winding from one end to the other and turned it on for about a second, maybe a second and a half, and read it. If the high voltage section shorts, it draws on the primary side about 4 and a bit amps. If you short the filament winding from end to end, it draws about 1.5 amps, something like that. And that's with the extent of the wires themselves acting as resistance. That'll change as, as you shorten the wires up and get closer to the transformer, because the wires are, acting as resistors at that point. It was shorted right across this point, and the B plus was shorted right at the actual transformer itself to determine that. So I'm giving myself about 0.5 amp, maybe just under 0.5 amp safe zone. Okay, so, 400 milliamps worth of safe zone here, and that's about it. Now, you can choose whatever fuse makes you feel comfortable. This is my own choice, and this is what I'm using right here. If you wanted to get closer to the absolute maximum draw, again, it was just around 600 milliamps, a little under 600 milliamps. So if you wanted to say 800, give yourself a bit of a safe zone there. That's fine. I chose 1 amp, again, for myself, because I don't want this to ever go away unless there is something very wrong with the amplifier. Okay, there's nothing worse than having a fuse go away if you're, say, playing somewhere or something like that. Just say you're going to take this to somewhere live and show it off, and you had this plugged into an external cabinet of some sort, and say you hit some heavy bass note or something like that, or, there's a power excursion and you hit a heavy bass note and it came close to the fuse value and it went away, you're basically out of business. You can't do anything until you take the amplifier apart and get to that fuse. Now, this fuse would have, another fuse holder on here and something that would be accessible from the back, but again, running out of chassis space, right? So this is underneath here. As you can see, it's shielded, and I marked the fuse value right on the actual shielding itself. So use what value you feel appropriate for you. If you want to make your own measurements and, come a little bit closer to the actual value, that maximum draw value, that is up to you. You can do these experiments on your own as well. Again, if you do anything, you're doing it at your own risk. Be very, very careful. Right? There is high voltage all over this thing. So, next thing, we have the negative bias section here, and you'll see that the full wave bridge rectifier here, because it's going from end to end on the secondary winding, is taking up that entire winding. So we can't use any of the taps on the factory transformer to, get a bias out of. So unless we could take the capacitor and tie it into these points, but what's the point? We may as well just go end to end and make things easy. So you can see there's a capacitor here that ties in, which allows us to create a separate bias supply. This resistor is needed so that the circuit works. And you'll see that the capacitors have the positive side of the capacitor to the chassis. Very, very important. Always make sure that the positive side of the capacitor in the negative bias section is to the chassis. It's very easy to get that confused with, regular thinking, because we're always thinking, this is the positive B plus line. The positive always goes towards that line, and the negative of the capacitor goes to the chassis. Well, in this case, because we have negative voltage here, the chassis is positive to that. So the positive of the capacitors have to go to ground. Always very, very important to remember that. It's very easy to get backwards. We've all done it. So this resistor here, you'll see on the schematic, on your version of the schematic, is just there to limit basically how far the bias will go towards the chassis. You can eliminate this and have full bias control. This just limits it off, and so that you just basically can't take it right to zero. So you'll always have some form of negative bias there. And again, that value is on your schematic. And in the amplifier, that value is right here. And this resistor right here across that potentiometer is right here. So you can technically look at that as just across this portion of the potentiometer right here. We have another filter here, and that runs directly up to these two resistors here that go to the control grids of the output tube here. What else can I tell you? I mentioned this before, the difference in the other schematic, because it was on a printed circuit board, to this, because this is point to point, because, you know, this is, you know, all wired up, and we have long lead length running to the FET here. You can see the long lead length. This resistor is absolutely necessary, so add that value in there, or you'll find out that this will run away and just do all sorts of very, very strange things. So do not forget to add that resistor in line with the gate lead of that FET right there. Let's see, what other notes do I have? This goes to the existing supply on the board here. So this is the resistor here, and that runs to the existing supply out of the rectifiers here. You can see this capacitor here is this capacitor right here. We have our biasing. Pay very close attention to these two resistors on the actual on the schematic that you have. Pay very close attention to those. Get this as close as you can, and that way you'll be able to bias this up. Now, if you want to be able to trim the bias, say you want to use a different transistor, maybe a bit more gain or something like that, what you're going to need to do is put a VR in this top side. You can leave this bottom resistor alone here that runs from the base to the ground. What you need to do is add a variable resistor in this line here to adjust the bias if you want to do that. So what you would do is you would cut this value in half and change the variable resistor to the same value as this resistor here. So you'd put a variable resistor in here, the same value as this, and you would cut this value in half. And that way you'd be able to sweep the entire range of the biasing, and you'd be able to try all sorts of different transistors if you'd like. Something to keep in mind if you want to add a variable, variable biasing to this, if you want to fool around with different transistors and higher and lower gain and things like that. I toyed with using a germanium transistor just for the fun of it, but again, that germanium transistor would be tough for all of you to find, so I wanted to keep this as easy to build for everybody that I could possibly make this. So I tried to use everything that is, available. Basically, everything is available on this. What else can I tell you? If you're going to use a feedback connection, if you reverse the plate leads, and you'll see the color of the plate leads listed on your schematic, and the color of these leads, everything is all listed there. If you reverse the plate leads, you'll get motorboating, you'll get an oscillator out of this thing. So you don't want to do that. You'll create an oscillator, so make sure that the plate, the appropriate colored plate lead that runs to this portion of the tetrode, follow this back to the pin on here and wire this exactly. Don't take these leads and flip them around, or you're going to have issues. So this will allow you to run feedback if you want. You can take the appropriate tap and then run a resistor over to this portion right here and give yourself feedback. Mind you, I don't think it's desirable. It makes the thing sound, it flattens the response and it flattens the sound. So it really does make a lot of difference. Now, if you're trying to make a high fidelity amplifier out of this thing, and you wanted to have really nice flat, basically curve, you wanted everything really, really flat, and to keep the frequency specs within a certain area, yeah, you'd want to add feedback to do that. But for this amplifier, without the feedback, it really adds personality. Let's calculate the open loop and closed loop gain of the vacuum tube portion of this amplifier. We'll ignore the solid state stuff for now just to keep this that much easier. It really isn't all that much harder. All we'd have to do is just move the scope probe to the base of the transistor here, and we could calculate even the gain of the transistor stage all the way through, but it's just easier. I have the scope probe hooked up to the input of the phase inverter, and it'll make it that much easier when I explain how to do the feedback calculation as well. It really is a simple process, and I find so many websites and people are just complicating this needlessly. It's very easy, and you'll see what I mean here. So I have my oscilloscope probe hooked up to the input of the phase inverter. So the signal's going through the amplifier, but we're only going to look at the gain of the vacuum tube portion of this amplifier. And it's not going to be much because it's just a phase inverter and an output. So one scope probe is hooked up to the input of the phase inverter, and the other scope probe is attached across the 4 ohm load. So trace A here is this probe, and trace B is across the 4 ohm load. In order to make this easy, I'm going to turn this up to about 1 volt. So I'm going to give this about 1 volt of drive. This is RMS here, AC RMS, both of these. Give it about 1 volt of drive, and we'll see what we get out. And it should give us just a very easy equation right there. So I'll turn up my signal generator right now. It's at 400 cycles. Okay, so I'm breathing on this control right now. Okay, I'll turn that down just a touch. Very touchy to get it right at 1.00. I'm probably being just a little bit too picky here. Very close. So we'll say 1 volt for 5.4 volts out. Okay, so 1.01, close enough. So 1 volt for 5.4 out. So I'll mark that down. So 1 volt for 5.4 out, okay? Now what I'm going to do is I'm going to connect up a feedback resistor. So this goes from the output right across that load. So it's going from the 4 ohm load to that feedback point. So now we have 1 volt for 3.17 out. 1 volt for 3.17. Call it 3.17, 3.18. That's okay. Close enough. Just turn that down. This is all we need to calculate everything. So it takes open loop gain here. It takes 1 volt to give us 5.4 volts out. Well, since we're driving it with 1 volt, we have a gain of 5.4. It's that easy. So the amplifier from the phase inverter right to the output has a gain of 5.4. Not a whole lot of gain, right? Because it's just a phase inverter. And then when we attach a 680 ohm feedback resistor in line, it drops that down. So we only have a gain of 3.17. Now what we want to do is turn this into dB. That's very easy. So what I'll do is I'll just put this down here. Hopefully the amplifier won't tip. Is it going to stay? It will. Okay, so grab your calculator. Very easily turn on the calculator. So you go 20 log, because this is a voltage calculation, you go 20 log 5.4. 5.4 equals 14.64 dB. Okay, so we write that down for the top. So 14.64. 14.64. Okay. So that's our open loop gain. So clear. Now we do the same thing with this. 20 log 3.17 equals 10.02. So you go 10.02. Just that simple. We pretty much don't even need a calculator to do this, but I'll do this. So you go 14.64, 14.64, take away 10.02 equals 4.62. By adding that resistor, we added 4.62 dB of feedback. For those of you that are curious how much gain this one transistor adds to the amplifier, let's find out. So I've moved the scope probe to the base of the transistor here, and the other probe is still across the load. So I'll just turn this up to a safe amount. About 5 volts before clipping should be fine here. I'll just turn that down, make it nice and easy. Around it anyways. So 0.012 volts in for 5 volts out. So I'll grab my pen. Let's turn that down. So 0.012 for 5 volts. Okay, so just so I can remember that, put this down here. So grab the calculator and we'll go 5 divided by 0.012 equals quite a bit more gain. Here's a closer view of where I tied the oscilloscope probe in to take that last measurement. That was an open loop gain measurement. So the oscilloscope probe was tied right to this portion right here. So this is the signal path from the amplifier here, through this capacitor up here, and then right into the base. And this little area is a nice, very easy place to tie into, so I could just clip the scope probe to this side. Another thing that I would like to mention here is before the amplifier is powered up, you should always make sure that you have maximum negative bias. So you want the maximum amount of negative voltage on the control grids of these tubes. So you don't want this potentiometer, the wiper, close to ground. You want it close to the negative bias supply to start with. So with this right up at the top, you're going to get about -75, -80 volts or something like that. Always start at the top and then bring it down slowly until you get a current reading. Again, this right here is the jack that runs out to the meter to read the current on. So you want to start turning this down towards the chassis slowly, and then as you get to around, well, it depends on the tube and how strong the tube is, it can vary quite a bit. So I'll say comfortably between -18 and -25 volts somewhere, you're going to start to see, the current is going to start to rise up. So as you come down, of course, like say 25, you're going to start to see a rise. And then as you go 24 or 23, then you're going to really start to see the current rise up on the meter. And then, down to, I think this one sits at about -22 volts. That's where this one tube sits. Now, different tubes, different strengths will, affect that. So if you have a different type of tube, you might find that it'll sit, if it's more sensitive, it might actually need to be turned up to -25 volts to, make it bias properly. Or if the tube might be a little bit more tired or something like that, you might be able to take it down to, say, -18 or something like that, right? So as you come closer to ground, so -18 is closer to ground than -25. As you come closer to ground, that current is going to rise more because the tube is turning on more as you bring it closer to ground. The more negative voltage that you put on the control grids of the tube, the more you're turning the tube off. So something to keep in mind, always start at the maximum negative voltage on the control grids. If in doubt, if you're going to try and build this project, if in doubt, measure the voltage at this point right here, or at the control grids. It's a little congested in here, but measure it at this point and make sure you have maximum negative voltage at this point. And then when you turn the amp on, you know that, okay, if, basically the tube is turned right off is what I'm trying to say. So if there's going to be any issues, at least the tube is turned right off. If you start this at the ground end and try and turn it up, you'll burn the tube out immediately, right? It's as soon as the filaments warm up, you'll just see that current meter just peg right off the end. And then of course you're going to start to create issues with your amplifier. So you always have to be careful. Now again, I added that limitation resistor down here in the bottom, right? So it stops the negative bias from going right to ground on this particular in this particular build here, but it's still close enough to ground that this will pull an excessive amount of current. So I left myself a lot of room to play with a lot of different tubes as I was experimenting. You can up this value of resistor here so that, maybe it bottoms out at, say, -18 volts or something like that if you want to protect yourself, right? So it just all depends on how you want to build your amplifier. A lot of people don't want any limitations. They want the bias to go wherever they want. They want it to go right from the chassis right up to negative whatever. So again, in this particular case here, and as illustrated on or drawn on the schematic, I've added a resistor in there so that it won't go directly to the bottom. Another very, very important thing to remember. Since the bias is taken through this capacitor off the secondary winding, off the B plus winding, do not ever shut the amplifier off. So say the amplifier is on. Do not ever shut the amplifier off once it's warm and then immediately turn it back on again. Do not do that. Because what happens with this particular circuit here is when you first turn this thing on, it takes a while for the capacitors to charge. It takes a few moments, I should say, for the capacitors to charge in the negative bias section. And if you shut it off and let the power supply drain off and the negative bias supply drain off, and then if the cathode in the tube, because it's got a really large cathode in that 6360, right? The cathode will probably still be in some form of emission. If you turn it right back on again, you'll find that the current meter will go way up for a moment and come right down again, and it's not good for that tube. Now, with the way this transformer is and the way that the rectification is, this capacitor is needed in that bias circuit in order to get that bias. So there is a bit of a delay. So if you were to turn the amplifier on, so you click the amplifier on and the thing warms up, you shut it off, I would count to about 10 or 15 seconds before you go about turning this thing back on. I would say 15 to be safely, and then turn it back on again. And that way the cathode inside the 6360 has cooled off. Now, in most cases where you have a secondary with a full wave rectification with two diodes. So the center tap of the transformer runs to ground, and then you have full wave rectification, not a full wave bridge rectifier, but full wave with two diodes, one at each end of the winding. You can take that bias usually, or you have bias from another point in an amplifier off another winding. Some of them have a separate bias winding, or, just depending on how this situation is. That particular bias scheme, when you don't have this capacitor here, charges those caps almost immediately. So you might get a bit of a flicker in the current and then it'll come back down again. But this, it takes, a moment or two for it to charge the filter caps, which is that filter cap there. And then this filter cap here is the other bias filter right here. It takes just a moment to get those things filled up, we could say, and it might be, a little bit hard on the tube. So something to keep in mind. Those are two very important things. Bias at the top end to start with, and don't ever shut the amp off and turn it back on immediately, or, even after 5 seconds or something like that. I'd say 5 to 7 seconds is, you're kind of really pushing your luck. I would give it about 15 seconds, something like that. The longer you can wait, the better. Wait till that cathode's cold in the 6360 and then turn it back on. And then by the time, it just takes a few moments for the filters to charge up. And then by that, it takes quite a while for the cathode to warm back up again, right? So the bias is well ahead of the emission. Let's put it that way. Something to keep in mind. That is valid for all of these type of bias schemes that are put together like this. Now, I thought of incorporating an actual screen cutout circuit. So basically it would knock the screen off, and then it would wait for, say, 10 seconds after turn on or something like that, and then it would apply the screens. But again, more circuit complexity, and I would need to design a board for that. And I want to keep this all point to point. I want to keep it as simple as possible. In the previous video, I had a few requests to do an A/B comparison between this amp and the transistorized version, or just to listen to this particular amplifier. And the issue with that is there's just too many variables between the amplifier and you. So for example, I would have to play music through this amplifier, and I would have to have my microphone in front of the amplifier. The sound would go through my mic, through my processing gear, into my camera, from my camera up to YouTube where everything gets compressed. And then on your side, it has to go from YouTube through your computer, through your sound card, to your speakers, or to your headset. And you can see between here and between there is a huge amount of error that could be introduced. And I don't want to give anybody the wrong impression of this amplifier. This amplifier sounds incredible, and I really don't want to possibly give the wrong impression due to some setting between my end and your end. So I'd much rather not do that. There would be a second issue as well. YouTube has royalty-free music. So you can get some form of music from YouTube's, basically copyright-free library. And I've listened to a bunch of it, and I gotta tell you that I would much rather not use that music. So the best thing to do, if you're going to actually build this, right, you're going to be listening to it yourself, you'll find out how good this thing actually sounds. In fact, this transformer would sound very, very good in a decent amplifier, just an amplifier with this and another gain stage. I swept this, and the transformer works very, very well in a very broad range of frequencies, and it sounds incredible in this. Absolutely incredible. Again, no comparison. So to give you an idea of how incredibly good this thing is, so when I had both of them together, I wanted to do an A/B test. So I set both of them up, and I had some music programmed into an MP3 player, and I also had a CD player as well. I ended up going for the CD player with a CD in it. So what I did is I set both amplifiers up, and I got my other half to listen to them. So what I did is I tried to make it so that my other half would favor the transistor amplifier. I played it first, all right? So I set all the controls on the face of this amplifier up exactly to the way the controls were on the transistorized amplifier. The only difference is that the gain on this had to be turned down just a little bit, because this has a little bit more gain, because I wanted the volume levels to be the same in the amplifier. So I tried just, to make her favor the transistorized one first. So I put the music into the transistorized one, and I played it for a while. And then I unplugged the jack, and I plugged it into this one. And I have to tell you, within 2 seconds, she pointed to this one and said, "That is the vacuum tube one. Hands down," she said. "That's the best representation of I can actually give you." So we're, both into music, and she just, within a couple of seconds, say, "There's no comparison. That one is definitely the tube one." And I was like, wow. So she had a really good long listen to the solid state version, and that's the best representation that I could possibly give. So if you build this thing, you'll understand. Now, if you're going to play music through this thing, the controls on the face, because the front end of this amplifier is designed to favor guitars. So they really did a lot of work on this to really favor the mid region. So I enhanced the bass with that capacitor that you see on the schematic. It's marked with the actual part number on the circuit board. I enhanced the bass response with this, and it does sound very good, but you have to play with the controls a little bit to make it sound really, really nice in, say, in a music atmosphere where there's more than just something that's mid. But other than that, because of the EQing, it's incredible, to say the least. It's incredible. I have plans to actually build a hi-fi amplifier with this tube, and I may try some other transformers. I'm not sure. I may just do some experimentation, sweep some other transformers. But this tube, it's incredible in audio service. This amplifier is just amazing. So down the road, we're definitely going to build a hi-fi version with the 6362. I think it would be kind of neat to build it with just one, and maybe push that plate voltage way up to the top, see what we can do with that 16360, see what we can actually get out of that 16360 safely, because even in this service right now, it doesn't even break a sweat with what it's doing here. And into full clipping, it was, 16.3 or 16.4 watts, and this amplifier is what I got out of it with everything set the way it is. And the tube didn't even break a sweat. Here's another really neat device that I'm going to be releasing here quite shortly. It's another piece of test equipment for your bench to make your troubleshooting procedures all that much easier. So here's how this thing works. If you can remember, red is positive, very easy. And if you can remember green is negative, you're set. This is a transistor tester and transistor identifier. Let me give you an example. So let's grab a random transistor on the side here. So this is a 2N3906. So this is a PNP transistor. Okay, so I'll plug this in. Now if you remember, red is positive and green is negative. PNP. It's flashing a solid color, so it's a solid green and a solid red. The transistor's okay. Move that out of the way. It's another random transistor that I just pulled out of a chassis, so plug this one in. Green is N, right? Negative, positive, negative, NPN. It's an NPN transistor. Now the LEDs could be configured so that they're, sitting in the middle like this. It's just the way I have this sitting on the board to make it easy to get my fingers in here, that's all. So NPN, and they're flashing a solid color, so it's okay. I'll remove that. Grab this one here. Another 2N3906, so it's another PNP transistor. I'll plug this one in. Now if you look at those LEDs, they're flashing like emergency lights. It's going red and green. That's a faulty transistor. It has a base to collector short. Pull that out. Grab another random transistor. There's a 2N2219. Plug this in here. It's kind of big. Hopefully it'll plug in here. There we go. NPN. It's an NPN transistor. Solid color. It's okay. So this is going to lead into another piece of test equipment that I'm already working on as well. I've got so many neat ideas to release here. So this will be coming up quite shortly. I ordered up a bunch of components and they arrived today. So those components are going to be used in this circuit to make it all that much better. So I'm still whittling away, I guess you could say, at this circuit to get rid of components and make it all that much easier to build. Now there's hardly any components in this circuit already. It's really, really taken down. This could be built on perf board or anything like that. And it's a very, very simple transistor identifier and tester, and it's very, very effective. So if you have boxes of transistors or just random transistors that you want to test out, there'll be a bunch of different areas for you to test different types of transistors and things like that. And that'll be coming up very, very soon. In fact, I'm excited to get working on it. I haven't even opened the box of components yet. The delivery fella just dropped it off. So let me get into that box of components and start working on this thing immediately. So I should have something for all of you very, very soon. All right, I hope you've enjoyed this video. If you did, you can let me know by tapping the heart symbol below, and I'll have lots more neat things coming in the future. Talk to you soon. Bye for now.